This is Docere Digest Podcast, breaking down health concepts. This podcast is brought to you by Docere Life Center. This innovative clinic is finding new solutions to the evolving challenges mankind faces in the 21st century. By utilizing cutting-edge technology and testing, they find root causes and also offer treatment with energy and nutrition. What is the mission? To dynamically change lives for the better while impacting families for generations. The information shared directly or indirectly in the Docere Digest podcast is not to be understood as or misconstrued as medical advice. This information is not a replacement for your current health provider who is acutely aware of your current health state and course of treatment. Any information shared about a product or service discussed by any host or guest on this podcast is not to be interpreted as a doctor-patient relationship.
Welcome back to another episode of Docere Digest. This is our fourth episode on epigenetics, which focuses on changes in DNA expression. In our previous episodes, we have talked about what epigenetics is, including how genes work, what are genetic mutations, and how we pass on epigenetic factors to our children. We also talked about the methylation map going through the urea cycle, the folate cycle, the methionine cycle, the transsulfuration cycle, if I can say that. And then we had an in-depth discussion on MTHFR. Last time we also talked about how genes can be turned on and off and how they can be influenced by diet, nutrition, stress, exercise, diseases, words, and frequencies. We encourage you to go back and watch those if you haven't already. Today we're going to talk about environmental factors that affect or influence genetic expression. So what is an environmental factor? The National Human Genome Research Institute, which is part of the National Institute of Health, says that environmental factors as related to genetics refers to exposures to substances such as pesticides or industrial waste where we live and work, or behaviors such as smoking or poor diet that can increase an individual's risk of disease or stressful situations. Some examples of environmental factors include pollution, pesticides, metabolic function, heavy metal exposure, prolonged screen time, UV light, trauma, whether physical or psychological, inflammation, nerve damage, and so much more. Basically, environmental factors are anything outside of the DNA that affects how your genes are expressed. Some of these changes will affect your traits, while some may not. Remember that many of these factors will influence the genetic expression by modifying how genes are methylated or not methylated. So I'm going to be covering external environmental factors, and most of our information regarding how these factors affect the genes comes from animal and plant life studies because of the complexity and ethics of trying to do similar studies in humans. But sometimes we can still make observational analyses, like with the Holocaust victims that we talked about last time, and the effects of stress and trauma. So one big factor or easy way to kind of get into this is looking at nuclear radiation. It's probably one of the biggest and most easiest to recognize when it comes to genetic interference or mutation. So obviously when we're talking about nuclear radiation, the biggest one's probably going to be Chernobyl. So this was when there was a nuclear reactor explosion that actually released 400 times more radioactive material into the surrounding environment than the atomic bombs dropped at Hiroshima and Nagasaki. So radiation caused genetic mutations and molecular damage in the form of oxidative stress, and we saw mutations occurring in plants and animals such as change in colors, change in leaf shape and structure. Insects we saw in firebugs in the area had genetic mutations that changed their appearance from a balance of red and black to mostly black with very little red, and they actually have kind of a charred look to them, like they've been burned by fire. Many animals that were born in the area after the incident had physical deformities, and we know during the incident, many people died from acute radiation sickness, and following that, there was also an increase in cancers in children in the region, especially thyroid cancers because of the thyroid sensitivity to the radioactive iodine. So obviously, nuclear radiation is an extreme case, which most of us won't face, but again, it highlights extreme changes that are easier to recognize. So some other factors that we deal with more regularly UV radiation is a big one. UV radiation can break strands of DNA by two classes of DNA lesions at the cyclobutane pyrimidine dimers, or CPDs, and 6,4 photoproducts, or 6,4 PPs. Both of these lesions distort DNA structure, which can alter transcription and replication. And flexible areas of the DNA are most susceptible. One big hotspot is the p53 gene, which supports gene stability and suppresses cancer growth. So that's why when we have a lot of UV exposure, skin cancer is one of the common things we see. Even without getting into the UV, light itself can actually cause changes. So there was an interesting experiment done on some caterpillars, two different types. There was the Vanessa urtica and the Vanessa Isle caterpillars, and they were kept in different environments, some under red light, some under green light, some under blue light, or some under no light. And when they became butterflies, they had dramatically different wing coloring. So the caterpillars that were raised under red light had vibrant, intensely colored wings. The ones that had green light had dusky or dark colored wings. Blue light or no light had paler or colored wings, and those actually tended to be larger than the other butterflies. So it's interesting to see how, even just in different areas of life, we can see different expressions of how something as simple as the presence of light or the type of light can affect the outcome or the development of that insect or butterfly to have different presentation. So what about humans? So when I think about this, I think about Alaska. Alaska has very different light patterns throughout the year, especially in the winter and the summer, either being light all the time or dark pretty much all the time. And this is really going to affect circadian rhythms. So if we go back to my talk about stress last time, I talked about cortisol. Cortisol is a big part of your circadian rhythms. We want a lot in the morning to help you wake up and get going, and we want less at night so you can actually fall asleep and get into that rest repair mode. So disruption to the circadian rhythm can disrupt many physiological processes such as brainwave patterns, hormone production and signaling, cell regulation, and more. Disruptions will hinder the normal rest repair activity at night, which leads to more stress in the body, which can affect gene expression like I discussed last time. So there's also research being done to generate DNA technologies that utilize protein engineering that create light-sensitive enzymes that can actually turn DNA sections on or off. So as they're looking at trying to incorporate DNA into different technological advances, that's one of the things they're actually looking at, is how they can use light to turn things on or off. So another one we commonly experience is going to be air pollution. We talked a lot about air quality in our interview with Mike Mead, and if you haven't seen that, I highly recommend you go back and watch that for tips to improve your air quality in your home. But a study regarding the chemical pollution compounds from the production of steel can actually influence genetic instability. It was noted that herring gulls near steel mills in Great Lakes areas had higher rates of genetic mutations. Studies done on mice in these areas assessed for how the pollution affects the genome showed that heritable mutations formed as a result of the pollution and were passed down to the offspring through the father. Several recent studies have also linked air pollution with DNA damage in human sperm. So it can go through and affect how well your sperm work, if you have infertility issues, and different factors that you may pass on to your children. Other studies show that air pollutants can decrease DNA methylation and affect the histone chromatin structuring patterns. There's studies that show that air pollution can also impact the developing lung and immune system, which increases the chance of asthma. One study in Europe actually estimated that the exposure to pollutants related to road traffic could be attributed to around 15% of asthma cases. So another thing we may not get in large quantities, but we do have exposure to through our foods is pesticides, which Dr. Luke, I think, talked about some in our last episode. So this is obviously going to be more pronounced for people that are in agricultural areas and are raising crops and using pesticides and all these things to protect their crops. from pests. But a study published 2 years ago in the International Journal of Environmental Research and Public Health demonstrates that pesticides can modulate the expression levels of different genes and induce different epigenetic alterations in the expression levels of mRNAs and the modulation of DNA methylation status. So again, this is more pronounced for farmers and people in agriculture areas, but this still can present through our foods if they're not cleaned and handled properly. Here's another interesting thing I saw is how temperature can affect certain genes. So I see this, or one study showed this in Himalayan rabbits that carry the C gene, which can be turned on or off depending on the temperature. So this gene affects pigment development in the fur, skin, and eyes. So this gene is turned off at temperatures above 35 degrees Celsius, leading to white fur, and the gene is most active between 15 to 25 degrees Celsius, which leads to black fur. What's really interesting is that the central or core parts of the rabbit's body is warmer around the organs, so these rabbits still end up with white fur on much of its body, even at those lower temperatures, but they tend to have more black fur along the extremities, ears, and even their nose. So another thing with 5G coming up, we have a lot of discussions around EMF fields. And we've known for quite a while that higher frequency EMFs like X-rays and gamma rays can cause DNA damage through ionizing radiation. I know Dr. Ben has talked for over a decade about how microwave and radio wave frequencies can lead to DNA damage, fertility issues, and other pathologies, including cancer. Almost all human-made EMFs include these extremely low-frequency bands, and complex radio frequency exposure from wireless antennas and devices are starting to show, or more studies are starting to show, that prolonged exposure to these waves can lead to DNA damage and consequent conditions. So what about 5G? Well, this can be a little tricky depending on the research you look at. There are a lot of conflicting opinions about this, and the research seems to be equally conflicted, but I do think there are some factors you can look at that would explain some of that confliction, but I do think it's important to note that in the last 6 years, 434 scientists and medical doctors from over 40 different countries have signed a 5G appeal trying to limit or stop 5G rollout in Europe. So what do you guys think about 5G?
Well, if history tells us anything, these frequencies always change or modify something in our body. We're not designed for these high frequencies at some of these concepts. And whether we say it's generational, meaning it takes time to adapt to them, we know it will have an effect that will eventually cause more damage to the future generations, make them more susceptible or stronger.
Yeah, I think time will tell the final answer for this, and I think we're going to see a lot more research coming out about this, especially in the years to come. But what I really want you guys to take away from this is there are many external environmental factors that we are exposed to on a daily basis. Some we can control, some we can't, but the more aware we become regarding those factors, the more steps we can take to limit the influence they have over us. With our testing, we can work with you to identify possible ways to control the level of influence these factors have over your genes and over your health. All right, so if there's nothing else, I'm going to go ahead and transfer it over to Dr. Luke to talk about internal factors.
Awesome. Thanks, Dr. Caleb. So throughout this epigenetic series, as it's been my want, I've listed out various genes, specific genes that have to do with various potential symptoms and conditions and what have you. And when it comes to what I want to talk about here, which is digestion, particularly of carbohydrates, proteins, and fats, if we were to list out all the genes that we have here specifically, I think that could be its own series in and of itself, with me rattling off all the different genes that have to do with how well one breaks down carbs, proteins, and fats.
And we'd put everybody to sleep.
We would. As that's been done to us.
They'd at least know their alphabet very well.
They would. So I'm not going to do that. This is going to be pretty short, sweet, and to the point because I really want you to have a good take home here and hopefully give you something to think about. So I'm going to use a line that Dr. Ben and Dr. Kyson imprinted on me from day one of me even discerning if I wanted to go become a chiropractor and doctor. And that is this. You've heard of the saying, you are what you eat. Well, in reality, this is only a partial truth. Rather, you are what you digest, absorb, and assimilate. meaning that eating the right things is only half the battle, if that. We must make sure that we are addressing whether or not that person has the ability to digest, which is break down the food, absorb the food, which is to enter into the bloodstream, and then ultimately be assimilated, which is taken up into the cell to become whatever it is that nutrient is going to become. Things like hormones, cell walls, new tissue, etc. So within the genome report, we do analyze how well the patient is positioned or predisposed to break down carbs, proteins, and fats that they are getting from their diet. And again, this is crucial. Let's give a couple of examples here. Take fats, for instance. Fats go on to become hormones, cell walls, and it is interesting to note that your nervous system is 60 to 80% fat. And then take proteins. Proteins go on to become immunoglobulins and antibodies, which are important for your immune system, sustaining tissue, muscle, tendons, ligaments, and the like. And the biggest one with carbohydrates is those get broken down into glucose, which is a single sugar molecule, which then goes on to help make ATP, which is, of course, our body's fuel for sustaining life. So, making sure we are, 1, getting adequate fats, proteins, and carbs from the diet. 2, we're chewing our food thoroughly and not shoveling our food down. I need to be better about that. And then 3, making sure we have the enzymes in place to help break down these macronutrients. So as the other doctors can attest to, digestive enzymes are often a fundamental yet crucial part of what we do. That's all I got for you guys. So with that, I'm going to go ahead and turn it over to Dr. Craig.
Wow. I don't know how I feel about this. That's too short. I wasn't quite ready. Just kidding.
Right.
Well, as usual, I'm the guy that gets kind of tie in the emotional aspect to this thing. And last time I was really more talking about how we influence kind of the input into our genetic interaction. Really, what I'm going to talk about is more about how we are impacted and we interact with our environment based upon our DNA makeup. So the first question I kind of ask myself is, okay, how does emotions relate to DNA? We kind of talked a little bit about it last time from the frequency aspect. Emotions are chemicals which are produced by the cell according to the DNA blueprint. So therefore, your DNA is going to impact your emotions. So the two main ones I'm going to talk about is the difference between sympathy and empathy. And so before we talk about how the genes impact that, let's talk about what these two words actually are. And I like this definition that I found is empathy is shown in how much compassion and understanding we give to another person. Sympathy is more a feeling of pity or sorrow for another. Empathy is our ability to understand how someone feels, while sympathy is our relief in not having the same problems. Interesting, isn't it? So when it comes to sympathy and empathy, we talk a lot about the OXTR gene, and we were talking about this off air of how many OXTR genes there are and how many impact what different things. And there's what, Dr. Bowers, more than 70 OXTR genes, and I'll let you go through all of them because I'm not going to list them all. Exactly. What I find interesting is the research I did is it's interesting how different ones of those impact different aspects of empathy and sympathy. Some are related to your romantic relationships, and some of them are related to more social, and some are related more to your kids, and some are related more to yourself. So it's just, I find it interesting again how fearfully and wonderfully we are made, that you have different little nuances of the genome that relate to different nuances of emotions and experiences and all that type of stuff. Here's kind of what I want to leave with. I think it's interesting how we have a predisposition, and Dr. Luke and I were actually even talking about this even beforehand, how you can have a predisposition and then you can have a different expression based upon your stress or non-stress level. Really, to me, what this comes down to is how do we interact with our environment? Do we connect with it, or do we resist it and pull away from it? Because empathy is more is connecting and interacting and having a relationship, whereas sympathy is more of, sorry about that, that's you, not me. I'm going to go on my own way. I'm going to be more disconnected, more isolated, and more my own person. So it's interesting how our genetic makeup can determine how we interact with those around us. So any extra thoughts on that, now that I gave you those two interesting definitions?
Thought you said it well.
I appreciate that.
It's
What?
kind of interesting how we all grew up with "suck it up, Buttercup," or "cowboy up, cowgirl up."
Mhm.
Different people would react to different concepts about that.
Or I'll
Right.
slap a hair lip on you. I heard that one quite a bit
Right.
growing
Yeah,
up. So
exactly.
Well, yeah, and you look at the generation now today is more, well, let's be concerned about their self-esteem, and let's coddle them and let's move them along, and what's the impact of that? Not only from what they experience, but what's actually happening to the genetic makeup that then's being passed on to the next generation. The other part I find very interesting, and we kind of talked about this a little bit off air, is what's the interplay between the spiritual, the mental, emotional, the physical? You have a genetic predisposition, and yet do you always choose to be sympathetic or empathetic based upon what you express? You kind of expressed, Dr. Bowers, that according to the DNA and the trauma, you can almost say what a person's going to do. It's that almost part that I'm fascinated by is, what about when you don't go according to your DNA? What about when you don't go according to your blueprint? What is it within us that makes us make that change? And can you sustain that change, or will you tend to fall back into your genetic predisposition? So with that in mind, I'm going to pass it on to you, and you can talk about those traumas.
Good. Thanks, Dr. Craig. So my topic today is, how does trauma and crisis affect our genome? So first of all, let me pre-warn you, this is normally an 8-hour seminar I would do that contains a lot of alphabetic soup terms like MAOA, CMT, BDNF, etc., OXCR that Dr. Craig just brought up, et cetera, as well as some pretty scientific heavy words. But I'm going to try to bring the main point about crisis and trauma to you in about 10 minutes. So let me reiterate from previous episodes that epigenetics is a study of how cells control gene activity without changing the DNA sequence. And I think that's critical that we understand that, because you can't really tell from someone's DNA per se as you can from the genome. By looking at the DNA sequence and the external and internal environments, we can begin to understand how our genes react to the influences by how it's read and then utilized in the body. So talking about trauma and crises that affect the genome, let me put it this way. First, let's consider that your life is a book. Your DNA is the unchanging 26-letter alphabet, at least in the English language, and the plot of your book is shaped by your experiences, which is an ever-changing part of your life. We would say that you are in a fluid state, always adapting. You're not like what a rock is. Now, we know that significant trauma can cause dramatic plot twists that don't change the alphabet, but it can change how your DNA expresses itself, thereby affecting your mood, your reactions, your health, and even your reactions to some very specific conditions. Epigenetics emphasizes the continual rewriting of our DNA story through experiences affecting how we engage with our world. Much like a story going through a revision process, crisis and trauma's effect on the genes can be adjusted as well. We may not change the alphabet, but we can help reshape the narrative in healthier ways, creating beneficial impacts for our families and future generations. As we've discussed in previous episodes, the DNA genome controls the function of each cell in our body, and epigenetic modifications to our genes changes the cell's function by switching that gene or those genes on or off. Every modification impacts the function on a cellular level. Researchers are discovering that these modifications may even be inherited from generation to generation via specific genetic material. This means that environmental factors like stress, episodes of crisis or traumas can impact not only your health, but also that of your family and future descendants. So continue with the book analogy. Epigenetics is like a library where your DNA is the books. Not every book is being read at the same time, and environmental factors like diet, stress, emotional issues, or the lack of support will act like librarians, deciding which books or genes are open and read. When you experience high stress and crisis or trauma situations, it's like the stress books and the victim mentality books are constantly being read, and that will impact your outlook and your health. However, just like we can choose a new or different book to read, as Dr. Craig always says, we can choose to look at things differently or adapt things differently. We can also change our environment. By altering our environmental factors, like choosing healthier lifestyles or getting specific treatments, we can change which books are being read by our DNA. Now, as we've been saying, our DNA doesn't change, but we can influence which parts are active and or reactive. So let's address how different crises can affect our genes. Previously in our stress series, we discussed adverse childhood experiences and childhood traumas that we call ACEs. Research studies on ACEs have concluded the 3 categories of adverse experiences. Number 1, childhood abuse, which includes emotional, physical, and sexual abuse. Number 2, neglect, including both physical and emotional neglect or lack of support. And number 3, household challenges, which include growing up in a household where there was substance abuse, mental illness, violent treatment of either the mother or a stepmother, parental separation and divorce, or a family that had an incarcerated household member. Those are the top 10 categories of ACEs. So you can see that stressful or traumatic events experienced in childhood or during adolescence can be driven by a broad range of life events, which also include physical injury, natural disasters, bullying, and childhood maltreatment. It has been reported worldwide that the average trauma exposure rate is 69.7% for both children and adults. In the United States, around 60% of adults have reported that they have experienced at least one type of ACEs in their childhood. We now know that ACEs or childhood trauma are associated with negative health outcomes, both mentally and physically. In fact, those who have been exposed to multiple types of childhood trauma show an increased risk of early mortality, which decreases their lifespan by up to 20 years. Physically, childhood trauma has been associated with increased risk of cardiovascular disease, autoimmune disease, gastrointestinal symptoms, poor dental health, obesity, and type 2 diabetes. Psychologically, childhood trauma is regarded as one of the major risk factors for different forms of psychopathology. More specifically, childhood trauma has been linked to post-traumatic stress disorder, or PTSD, insomnia, anxiety, depression, bipolar disorder, maladaptive daydreaming, hallucinations, borderline personality disorders, disruptive behavior, risky behaviors, substance abuse, antisocial behavior, and eating disorders. Wow. We also know that childhood trauma impacts children to different extents. Some people are more vulnerable, where others show the characteristics of resilience with the ability to bounce back even after adversity. We've seen that in a lot of different sports events and other things that go on in our world. Multiple factors like genetics, epigenetics, and environmental factors and their interreactions contribute to the differential health outcomes induced by that childhood trauma. We now know that these types of traumas suggest that there may be other mechanisms contributing to these cells, such as different gene interaction, or what is referred to as genetic crosstalk, as well as by environmental reactions and epigenetic mechanisms. So how about you, the listener? Does any of this hit close to home for you or someone you know? Well, if the research is accurate, there's about a 60% chance that it does. And all this is now being addressed as genetic trauma. Genetic trauma refers to the effects of trauma that we inherit from previous generations, and the ACEs that we experience may be passed on to future generations through our genetics. Let me state here that trauma can be difficult to recognize because it manifests itself differently for almost everyone. And traumatic experiences can take many forms, as a traumatic experience for one person may not be as traumatic for another. We also know that male and female gender differences exist here as well. And stress-related psychiatric disorders, there are gender-associated differences in incidences, symptoms, and treatment response. For example, in PTSD people, the lifetime prevalence in females is 2 to 3 times higher than that in the males. Similarly, depression is more common in females than males. Interestingly, though, gender-related concepts contribute to these differences. There are multiple reasons that may explain this, such as differential traumatic exposures, cognitive factors, coping strategies, and biological factors between the different sexes. There are also fundamental sex-dependent brain differences between males and females. For example, the size of certain specific neurons. And we know that when dealing with stress, males and females present different specific patterns. Research has shown that when facing stressful events, men showed greater activation of their right amygdala, whereas women showed greater activation of the left amygdala. In addition to that, brain connectivity in response to stress also differs by gender. There's greater connectivity in certain areas of the brain that is different in males than in females after stress. Males present overactivation and increased connectivity in one area, whereas females show overactive and possibly enlarged different areas of the brain. In addition, males lose more brain cells after stress than females do. There's probably a real life joke here, but I think I'll pass on that one.
What'd you say? I don't remember.
Yeah, exactly. These gender differences contribute to differential fear processing, emotional regulation, and decision-making processes. So we know that males and females cope with stress differently. No wonder there are so many different reactions to the very same stressor. For example, when facing traumatic stress, females tend to be more emotionally focused and they use more palliative coping skills than males do. Also, females tend to seek social support more and benefit more from some specific therapies. Epigenetic modifications are also involved in setting up hormones and the maintenance of sex differences in the brain even before puberty. So females have significantly higher levels of methylation and estrogen receptors than males do. Interestingly, these sex-dependent epigenetic changes are dynamic across the entire lifespan of the person. There are also neurotransmitter-specific effects in gender differences. For example, in one study, the availability of the dopamine receptor has been associated with childhood trauma and pleasant drug effects, meaning that in males, there's a positive association between childhood trauma and pleasant drug effects, but not in females, which suggests that there may be sex differences in the reward pathway after a childhood trauma. Maybe this is why more males seek for chemical stimulation to shut off the stressors and to seek more pleasurable pathways. Autonomic systems are also different between males and females, which may also contribute to sex differences in stress-induced gene reactions. Research has also shown that women with a history of childhood trauma have a higher methylation process of the dopamine receptor, which causes them to develop an eating disorder versus those without such a history. So genetic SNPs play a significant role here, and we have to understand that. What's less understood or talked about is how all of this impacts the next generation. Research has found that stress during pregnancy is one generational trauma that can be passed down. The research has shown that parental stress seems to affect males more, and postnatal stress affects females more. They also found an association between prenatal trauma and PTSD, anxiety and depression, and those children that were born from that circumstance. In fact, twins, as they did some studies on twins, they found that there was a 30 to 70% increase of PTSD without any known trauma that suggests that some of these aspects of trauma may be inherited. Researchers have developed a generational impact of trauma on children of people who lived through the Dutch famine in what's called the Hunger Winter during World War II. And Dr. Caleb talked about some of these things on the, what was the word I was just looking for?
For the Holocaust.
The Holocaust. Here in just a moment, I'll go into some of that. But these were all around the World War II. So several studies found that the children of pregnant women during this famine were more prone to a higher than average body mass and diabetes. They also found that prenatal famine was linked to lower mortality. Scientists discovered that babies who had been in utero during the severe famine times were born heavier than average. It is theorized that starving mothers automatically adapted the expression in their unborn babies of a gene involved in storing or burning fuel. These children had high rates of obesity, diabetes, cardiovascular disease, and schizophrenia in their middle age. Upon further investigation, it was discovered that they carried a specific epigenetic signature on one of their genes that caused all this. Scientists have also found that trauma can have a generational impact when they study the children of the Holocaust survivors. Studies show that some children of these Holocaust survivors experience sleep disturbance and nightmares in which they are being chased, persecuted, tortured, or annihilated as if they were reliving the Second World War, even though they hadn't even been born yet. during that time frame. Third generation studies have shown that grandchildren of Holocaust survivors showed higher traits of anger and perceived others and themselves less positively, and were rated by their peers as having lower socio-emotional functioning abilities. Other research studies have shown that the structural aspect of slavery and racism, along with the cumulative trauma in the United States, has been a fundamental driver of the generational transmission of stress, anxiety, and depression for those from those aspects. Trauma can leave a chemical mark on a person's genes, which can then be passed down to their offspring. The mark is not a mutation, but a change in how the gene is expressed. Epigenetic research has found a wide range of evidence that stress and trauma can alter gene expression. This ranges from a gene linked to the release of cortisol, as Dr. Caleb talked about, which is involved in the fight, flight, or freeze reaction, to a gene that's involved in fat storage or fuel burning utilization. So, how do we heal ourselves from genetic trauma? Healing trauma is very important, but not easy to do, and certainly something that at this point we don't completely understand at the biological level as of yet. There's still a lot of work to be done, but here's what we do know that has a dynamic impact. Seek out and explore positive environments. Remember that both positive and negative environments impact our brain and our epigenome. Thanks to neuroplasticity, our brain can change, and exposure to positive environments helps our genes change. Try to expose and immerse yourself in positive surroundings and healthy relationships where your needs can be met. Facing any form of trauma is incredibly hard, and perhaps especially so when the trauma derives from your family of origin. No one can be expected to demonstrate growth or recovery before they're ready, especially in the face of trauma. There's a book that I recommend you read by Mark Woolen, and it's called It Didn't Start With You: How Inherited Family Trauma Shapes Who We Are and How to End the Cycle. This book shows how the traumas of our parents, grandparents, and even our great-grandparents can live in our unexplained depression, anxiety, fears, phobias, obsessive thoughts, and even physical symptoms. So my key takeaway from all this is I want to tell you that your pain or genetic issues may not have started with you or because of you, but they can end with you if you get the help that you need. I'm going to ask you to please let us help you in any way we can. And now let's turn this over to Dr. Kyson so he can explain some other interesting environmental reactions. Dr. Kyson?
All right. Thank you, Dr. Bowers. So we're going to go back and we're going to talk a little bit more about peroxynitrite. So what I want to do is I want to kind of recover a little bit of what I talked about last time. Peroxynitrite, or also known as nitrogen dioxide, is an endogenous, so inside the body, reactive nitrogen species formed when a superoxide radical or reactive oxygen species connects with the nitric oxide. And whilst this reaction can cause all kinds of issues in protein amino acids, forming protein carbonyls, reactive nitrogen species such as nitrosilate, and other protein amino acids, it can cause a lot of neurological damage. So, study that I was reading on neurodegenerative disorders and the role of peroxynitrite said the inflammatory reaction is thought to be an important contributor to neuronal damage in neurodegenerative disorders such as Alzheimer's disease, Parkinson's disease, multiple sclerosis, amyotrophic lateral sclerosis or ALS, and Parkinsonism dementia complex of Guam. So not familiar with that one, but among the toxic agents released in the brain tissues by activated cells. So we must focus attention on peroxynitrite. The product of the reaction between nitric oxide and superoxide, peroxynitrite is a strong oxidizing and nitrating agent that can react with all classes of biomolecules. So all the biomolecules in our body can be affected by this, especially in the central nervous system. It can be generated by microglial cells, activated by pro-inflammatory cytokines, or also known as beta amyloid peptide, or beta A, and by neurons in 3 different situations. So these are the situations I want to talk about here. So the first is hyperactivity of glutamate, neurotransmission, and mitochondrial dysfunction. Second is going to be the depletion of L-arginine or tetrabiopterin, also known as BH4, or for better health. These first 2 situations correspond to cellular response to initial neuronal damage. so trauma. And the peroxynitrite formed only exacerbates the inflammatory process. Whereas in the third situation, the peroxynitrite generated directly contributes to the initiation of the neurodegenerative process. Would you like to know more? So let me break this down a little bit here, because that was a lot of gobbledygook if you don't know what we're talking about. So situation number one, let's break it down. So hyperactivity of glutamate neurotransmission and mitochondrial dysfunction. So excitotoxicity of calcium in the mitochondria. There's a thing called a triad of synaptic neurodegeneration. So while glutamate is the most common neurotransmitter in the mammalian central nervous system, wow, acting to mediate excitatory neurotransmission. However, when high levels of glutamatergic input elicits excitotoxicity, they can contribute to neuronal cell death following acute brain injuries such as a stroke or a trauma. Excitotoxic cell death has also been implicated in the neurodegenerative disease models. The role of the acute apoptic cell death in the setting of chronic neurodegeneration is still being investigated. So there's some debate on some of this, but it's still being investigated to try to prove it out. Evidence for sublethal, so it's not going to kill you, but it's going to make you wish you're dead almost, lethal excitatory injuries in relation to neurodegeneration associated with Parkinson's, Alzheimer's, ALS, Huntington's. In contrast to classic excitotoxicity, there's emerging evidence that implicates the dysregulation of mitochondrial calcium in excitatory postsynaptic neurodegeneration. The second thing here is depletion of L-arginine or tetrabiopterin. So within the nervous system, tetrabiopterin, BH4, are also known as?
For better health.
There you go.
For better health.
Is an essential cofactor for dopamine and serotonin synthesis. These are two of our major neurotransmitters. In addition, BH4 is now established to be an essential cofactor for all isoforms of nitric oxide synthase, or NOS. Inborn errors of metabolism affecting BH4 availability are well documented, and that the clinical presentation can be attributed to a paucity of dopamine and serotonin and nitric oxide production or generation. So looking at BH4 and seeing how oxidative catabolism and the observation of when BH4 is limited to some cellular sources of NOS may generate a superoxide, while other BH4 saturated NOS enzymes may be generating nitric oxide. Such a scenario could favor peroxynitrite generation. If peroxynitrite is not scavenged by antioxidants such as reduced glutathione, remember glutathiones are a master antioxidant, so something we need a lot of, irreversible damage to the critical cellular enzymes could ensue. Such targets include components of the mitochondrial electron transport chain. This is where you make ATP at the very end, the energy we need. You could have issues with alpha-ketoglutarate dehydrogenase and possibly pyruvate dehydrogenase. Lots of enzymes here. Such a cascade of events has been hypothesized, and it is seen to occur in the neurodegenerative conditions such as Parkinson's and Alzheimer's. So very big here when we're dealing with that. So let's talk about the third thing here. So the third one is peroxynitrite is generated directly and contributes to the initiation of a neurodegenerative process. So in inflamed tissues, the reaction of nitric oxide and superoxide leads to the formation of the peroxynitrite. So when we look at peroxynitrite written out in a chemical formulation, it's ONOO, also known as Oh no! Which is well-known oxidizing and nitrating agent, as we talked about. So the peroxynitrite formed can attack a wide range of biomolecules via direct oxidative reactions or indirect radical mediation or mediated mechanisms, thus triggering cellular responses leading to cell signaling, oxidative injury, and committing cells to necrosis or apoptosis, so the cellular death. Cellular DNA, which is important for us, is a target of ONOO, or peroxynitrite, and can react with deoxyribose, nucleobases, and do single-strand breaks. The free radical mediated damage to proteins results in the modification of the amino acid residues, cross-linking the side chains and fragmentations. Wow, that's a lot. basically what I like to do when I think of that one is I think of it looks like a blueprint of how things should be made, and somebody spilled coffee on it or sparks came off the welder and caught parts on fire. So we don't quite know how it's supposed to be built, but we got an idea, but it doesn't work out well. Things fall apart. So basically your blueprints are under attack, and you're going to be missing pages, you're going to be missing sections, or there's going to be just empty holes in the entire blueprints. So it's kind of what we're talking about here with how this is doing that. So let's see, where is that? The formation of neurotransmitters represents a specific peroxidite. Cut that. I missed a line there. It's not neurotransmitters. Oh, it's NT is nitrotyrosine. I'm like, it's not right. Okay. Ready?
Yeah.
All right. So the formation of nitrotyrosine represents a specific peroxynitrite mediated protein modification, and the detection of this in proteins is considered a biomarker for the endogenous, so again, inside the body, peroxynitrate activity. The peroxynitrite-driven oxidation and nitration of molecules may lead to autoimmunity and age-related neurodegeneration diseases. Hence, peroxynitrite, modified DNA, and nitrated proteins, and that can act as neoantigens and lead to the generation of autoantibodies against self-components and autoimmune disorders, and lead to all kinds of neurological issues. So that's what I have for today. Anything else? I know that was a lot, but that's a very big subject with the neurodegeneration that we're seeing a whole lot more of, especially as our baby boomers start booming toward the end of their life. We're going to see a lot more of this here. So how do we help these people live a long and healthy life? And it's crippling. How do we get them to be able to deal with that? So going through and looking at some of these things is very important. So, and that's all I have for today. Join us next time as we talk about polymorphisms and adaptability.
Thank you for listening to the Docere Digest podcast. If you enjoyed this episode, please be sure to subscribe and leave us a review. You can also find all the episodes and show notes over at docerelifecenter.com. While you're on the website, also be sure to check out the blog where you'll find videos and articles to help you proactively rebalance your health.